The sun doesn't ask permission before it reshapes your world. Right now, while you're listening to this, a wall of superheated plasma is screaming toward Earth at 2 million miles per hour. 24 hours. That's all we have left. And here's what nobody's telling you. The earthquakes have already started. Japan shook. Mount Etna cracked open. Alaska is trembling in ways that historically precede the kind of events that redraw maps. But according to some researchers analysing the raw data, this isn't one solar storm approaching us. It's two stacked like cosmic dominoes, ready to compress Earth's magnetic shield in ways the official forecasts aren't accounting for. Subscribe and follow along, because the flare has launched, the plasma screams across the void, and we're only watching the curtain rise on Act 1. The astronomical configurations framing this moment haven't finished their dance. January 3rd will bring answers, yes, but it will also unveil questions we haven't yet learned to ask. The clock is ticking. 24 hours from now, Earth will take a direct hit from a high-density plasma blast travelling at speeds that would make your jaw drop. We're not talking about some distant cosmic event that astronomers will study for years. We're talking about right now, about tomorrow, about a wall of superheated solar material screaming toward us at roughly 2 million miles per hour. And here's the thing that should make you sit up and pay attention. While you were sleeping last night, the earthquake's already started. On December 31st, 2025, at exactly 13:51, Coordinated Universal Time, the sun burped. That's the casual way to describe what the National Oceanic and Atmospheric Administration Space Weather Prediction Center officially logged as an M7.1 X-ray solar flare. Now, M-class flares sit in the middle of the solar tantrum spectrum. They're not the gentle B or C-class whispers, and they're not the civilization-threatening X-class monsters that make scientists genuinely nervous. They're the Goldilocks zone of solar violence, powerful enough to notice, rare enough to matter, and perfectly positioned to mess with our day in interesting ways. But this flare didn't come alone. When that burst of radiation erupted from active region 4324 on the sun's surface, it kicked off something else entirely. A coronal mass ejection. Imagine 1 billion tons of magnetized plasma, a soup of charged particles so hot they've forgotten what atoms are supposed to look like, getting launched into space like a cosmic shotgun blast. The NOAA models tracked it immediately, calculated its trajectory, ran the numbers, and issued a geomagnetic stormwatch rated G1 to G2 for January 1st through January 3rd, 2026. Official, documented, filed under routine space weather event. Except there's a problem with that official story. Some researchers looking at the raw data are seeing something the sanitized forecasts aren't highlighting. They're seeing two distinct plasma fronts, not one. They're seeing what they're calling a double stack event. A slower, denser cloud of solar material crawling toward Earth, with a faster, more aggressive burst coming up right behind it. Ready to slam into the back of the first one like a cosmic pileup on an interplanetary highway. If they're right, and that's a big if we need to be honest about, then what hits us tomorrow isn't a single wave. It's a compression event. It's plasma getting squeezed, concentrated, amplified in ways the standard models don't account for. And right on cue, as if reading from some apocalyptic script, the Earth started shaking. Japan registered a magnitude 6.0 earthquake, not huge by Japanese standards, where they build skyscrapers that can dance through much worse, but notable for its timing. Mount Etna, that moody Italian volcano that's been Earth's pressure release valve for thousands of years, cracked open a new fissure, fresh lava, fresh venting, fresh reminder that the planet beneath our feet is very much alive and very much paying attention to something. Then there's Alaska. Alaska is where things get genuinely concerning, because Alaska sits on one of the most volatile tectonic boundaries on the planet. It's part of the Ring of Fire, that horseshoe of volcanic and seismic violence that encircles the Pacific Ocean like a warning sign written in magma and crushed rock. And right now, as the solar storm barrels toward us, Alaska is experiencing what seismologists call a swarm. Not one quake, not two, dozens, hundreds. Small tremors, yes, but clustering in patterns that historically have preceded much, much larger events. The kind of events that redraw coastlines and rewrite history books. Now, let's be absolutely clear about something before we go any further. Because honesty matters more than drama. Mainstream science does not support a causal link between solar flares and earthquakes. the geophysical community will tell you correctly that tectonic movements are driven by processes happening dozens of miles beneath your feet, where heat and pressure and the slow grinding of continental plates operate on timescales that make human lifespans look like eye blinks. Solar radiation, they'll say, doesn't penetrate deep enough, doesn't carry enough energy to the right places, doesn't interact with rock in ways that would trigger seismic events. The correlations people notice are just that. Correlations, coincidences, pattern-seeking brains finding connections in random noise, and yet the timing keeps happening. Solar maximum periods coincide with increased seismic activity just often enough to make you wonder. Geomagnetic storms overlap with volcanic eruptions just frequently enough to raise eyebrows among researchers who aren't afraid to ask uncomfortable questions. Is it possible we're missing something? Is it possible that the intricate dance between the sun's magnetic field and Earth's magnetic field creates subtle influences we haven't fully mapped yet? Is it possible that charged particles interacting with the ionosphere could, through mechanisms we don't understand, modulate stresses in ways that push already loaded tectonic systems over some invisible threshold? These are questions, not answers. These are investigations, not conclusions. But they're questions worth asking, especially when you look at the bigger picture forming right now. Because this isn't just about one flare and one storm. This is about timing on a scale that makes even skeptics pause. We're entering the Chinese Year of the Fire Horse, an astrological designation that happens once every 60 years and carries with it centuries of cultural significance and, some would say, ominous historical precedent. We're also experiencing what astronomy enthusiasts are calling the alignment of the century, a configuration of planets that, while having no known physical mechanism to affect Earth, certainly captures the imagination and the attention of anyone looking up. Put it all together, a potentially double-stacked solar storm arriving in 24 hours, multiple seismic events clustering around the same time window, cultural and astronomical markers suggesting uniqueness. And suddenly you're not looking at isolated incidents anymore. You're looking at a pattern, maybe a meaningless pattern, maybe a pattern that reflects our desperate human need to find order in chaos, or maybe, just maybe, a pattern that suggests something bigger is unfolding. The last time Earth experienced a truly transformative geophysical moment on a massive scale was 1906. The San Francisco earthquake didn't just destroy one city. It triggered a cascade of scientific revision about how we understand fault systems, stress accumulation, and the interconnected nature of crustal dynamics. It was a domino that fell and revealed how many other dominoes were teetering, waiting for their turn. Are we standing at the edge of another 1906 moment, but on a global scale instead of a regional one? Tomorrow, the plasma arrives. Tomorrow, Earth's magnetosphere will compress, flex, and respond in ways we can measure and monitor. Auroras will dance across skies where they rarely appear. Satellites will hiccup. Radio communications will get weird. And somewhere, deep in the planet's crust, stresses that have been building for decades or centuries will either hold steady or find their release. The question isn't whether these events are connected through some grand cosmic mechanism. The question is whether we're paying enough attention to what's actually happening to know the difference between correlation and causation, between cosmic coincidence and something far more profound. The numbers don't lie, but they don't always tell the whole truth either. When the National Oceanic and Atmospheric Administration issued their geomagnetic storm watch for January 1st through January 3rd, 2026, they tagged it as G1 to G2 on their 5-point scale. Sounds manageable, right? Sounds like the kind of space weather event that happens a few times a year, causes some pretty auroras, maybe messes with GPS for a few hours, and then everything goes back to normal. The official models tracked the coronal mass ejection as it left the Sun, calculated its speed at roughly 1.5 million miles per hour, projected its arrival time with their sophisticated algorithms, and filed the appropriate warnings. Standard procedure, textbook response, nothing to panic about. But here's where things get interesting. And by interesting, I mean potentially alarming in ways the sanitized public forecasts aren't designed to communicate. The G-scale that NOAA uses measures geomagnetic storm intensity based on something called the K-index, which tracks disturbances in Earth's magnetic field. G1 means minor fluctuations. Your power grid yawns. Your satellites might need a software patch. Your ham radio enthusiasts notice some static. G2 bumps things up slightly. Transformers might need monitoring. Spacecraft operations get a little trickier. Auroras creep down to mid-latitudes where they don't usually appear. Still nothing that keeps emergency management officials up at night. The thing about these scales is they measure what actually hits us, not what's travelling toward us. They measure consequences, not causes. And the causes, the actual physics of what's screaming across 93 million miles of interplanetary space right now, tell a more complex story than a simple G1 to G2 rating suggests. Solar wind, under normal circumstances, flows past Earth at a leisurely 300 to 400 kilometers per second. It's a constant stream of charged particles, the sun's atmosphere constantly bleeding into space, creating what scientists call the heliosphere. Earth sits inside this bubble like a marble in a bathtub, mostly protected by our magnetic field, mostly insulated from the worst of what the sun throws at us. When a coronal mass ejection launches, those speeds spike dramatically. We're talking 600, 700, sometimes over 1,000 kilometers per second. The plasma density increases by orders of magnitude. Instead of a gentle breeze of solar wind, you get a tsunami. And this tsunami carries with it something crucial that determines whether Earth barely notices or gets absolutely hammered: magnetic field orientation. Every coronal mass ejection has its own internal magnetic structure, frozen into the plasma as it erupted from the sun. If that magnetic field happens to point southward when it reaches Earth, in the opposite direction of our planet's natural north-pointing field, something remarkable happens. The two fields connect, they couple, and suddenly, instead of our magnetosphere deflecting the solar storm around us like a rock in a river, it opens doorways that allow energy to pour directly into our upper atmosphere. This is what space weather forecasters obsess over. This is the variable that makes or breaks their predictions. They can track a coronal mass ejection speed with reasonable accuracy. They can estimate its density based on how it looks in satellite imagery, but they can't know its magnetic orientation until it arrives at the L1 Lagrange point, a gravitational balance point about 1 million miles upstream from Earth, where monitoring satellites sit and wait. By the time those satellites measure the magnetic field direction, you've got maybe 30 to 60 minutes of warning before impact. It's like trying to predict a hurricane's strength when it's already at your doorstep. The official NOAA forecast assumed a reasonably standard magnetic structure for this coronal mass ejection. They plugged in typical values based on the flare's characteristics and the way the eruption looked in solar imagery. Their models produced arrival times with error bars of plus or minus 12 hours, because predicting exactly when a billion-ton cloud of plasma will reach a specific point 93 million miles away involves so many variables that even supercomputers shrug and add uncertainty ranges. They projected moderate effects, prepared the appropriate technical communities, and moved on to monitoring the next active region on the sun's surface. But some researchers looking at the raw data saw something else. They saw signatures in the coronagraph images, the special telescopes that block out the sun's bright disk to reveal the fainter corona, suggesting not one cohesive coronal mass ejection but two distinct plasma structures. The first, slower and denser, erupted slightly earlier. The second, faster and more energetic, launched behind it like a cosmic afterthought. If both are real, if both are actually heading toward Earth on converging paths, then what arrives tomorrow isn't a standard impact. It's a compression event. The faster plasma would catch up to the slower plasma, pile into it, create a shock front with characteristics that none of the standard models account for because they're not designed to model multiple interacting plasma streams. This is speculation, and it's important to be absolutely clear about that. The official forecast from NOAA doesn't mention dual coronal mass ejections. The Space Weather Prediction Center's models show a single event, but the possibility raises questions about what we might be missing when we simplify complex solar phenomena into neat categorical boxes. Are there signatures in the data that suggest higher plasma densities than predicted? Are there subtle timing anomalies that hint at overlapping structures? The frustrating answer is maybe. The solar corona is a chaotic, turbulent environment where magnetic fields twist and snap and reconfigure themselves in ways we're still learning to interpret. Multiple eruptions can happen in quick succession from the same active region. They can merge in interplanetary space. They can remain separate but arrive close enough together that their effects overlap. What would a double-stacked impact actually look like? The first plasma front would compress Earth's magnetosphere, push the boundary inward from its normal distance of about 10 Earth radii down to maybe 7 or 8. The magnetosphere would start processing that first wave of energy, funneling particles along magnetic field lines toward the poles, lighting up auroras, driving currents in the upper atmosphere. And then, while the system was still responding to that first assault, the second front would hit. It would compress an already compressed magnetosphere even further. It would inject additional energy into radiation belts already enhanced by the first wave. It would create a sustained period of disturbance instead of a single spike followed by recovery. The effects wouldn't be uniform across the planet. This is another nuance the simple G-scale ratings don't capture. Geomagnetic activity concentrates at high latitudes, where Earth's magnetic field lines dive down toward the poles and provide a direct route for solar particles to reach the atmosphere. If you're in northern Canada or Scandinavia or Antarctica, you're in the prime impact zone. Auroras dance overhead not because they're pretty, but because they're visible evidence of Earth's atmosphere getting absolutely pummeled by charged particles. Radio blackouts happen because those same particles ionize the upper atmosphere, creating layers of interference that high-frequency communications can't penetrate. But equatorial regions aren't immune. The magnetosphere's compression affects the entire structure. Satellites in geosynchronous orbit sitting at about 35,000 kilometers altitude, where they normally orbit in the magnetosphere's protective embrace, can suddenly find themselves outside that protection, exposed to the full fury of the solar wind. Their electronics get hit by particle radiation. Their solar panels degrade slightly faster. Their computers can experience single event upsets, cosmic rays flipping bits in memory that can cascade into system failures if not caught quickly enough. The models that predict all of this are sophisticated, running on some of the most powerful supercomputers available to space weather researchers. They simulate the solar wind interaction with Earth's magnetosphere using magnetohydrodynamics, equations that describe how electrically conducting fluids behave in magnetic fields. They've been refined over decades of observations, validated against historical storms, tuned to match what actually happens when coronal mass ejections hit us. And they're really good at predicting standard single-event impacts, but they have blind spots. They don't handle multiple overlapping structures well. They struggle with unusual magnetic configurations. They can't account for what they're not designed to see. So when tomorrow comes and the plasma arrives, we'll watch the real-time data streaming from those upstream satellites with unusual attention. We'll see if the magnetic field points south and opens those coupling doorways. We'll see if the density spikes match predictions or exceed them. We'll see if there's any signature of a second structure following behind. And Earth's magnetosphere will respond however it responds, indifferent to our models and predictions and carefully calculated uncertainty ranges. The question isn't whether the models are wrong. The question is whether reality is more complex than the models assume, and whether that complexity matters for what happens next. The earthquake hit Japan at a time that made people notice. The magnitude 6.0 struck in a region accustomed to seismic activity, where building codes treat earthquakes like weather, and everyone knows the emergency procedures by heart. But the timing, coming just hours after the M7.1 solar flare erupted from the sun, set off a different kind of alarm in certain circles. Online communities that track both space weather and geological events lit up with speculation. Forum posts multiplied. YouTube channels prepared emergency videos, and the question that always emerges in these moments rose again. Can solar activity trigger earthquakes? The short answer from mainstream geophysics is no. The slightly longer answer is probably not, almost certainly not, and anyone claiming definitive causal links is either misunderstanding the data or selling something. Earthquakes happen because tectonic plates grind against each other under immense pressure. The mechanisms involved occur 10, 20, sometimes hundreds of kilometers below Earth's surface, where temperature and pressure create conditions so extreme that solid rock flows like putty over geological timescales. These are processes driven by Earth's internal heat, by the decay of radioactive elements deep in the mantle, by convection currents that move continents millimeters per year with the patience of planetary forces that operate over millions of years. Solar flares, by contrast, release electromagnetic radiation that reaches Earth in 8 minutes and interacts primarily with the upper atmosphere and ionosphere. X-rays and extreme ultraviolet light get absorbed dozens of kilometers above the surface. They heat the thermosphere, create temporary disturbances in radio propagation, and then dissipate. The energy involved, while enormous by human standards, represents a tiny fraction of what would be needed to influence tectonic processes. It's like trying to move a mountain by shining a flashlight at it. The scale mismatch is so extreme that most geophysicists don't even bother investigating the connection, because the physics simply doesn't support a mechanism. But then there are the correlations. Statistical studies have been conducted, some published in legitimate journals, others circulating in preprint servers awaiting peer review, looking at decades of seismic data alongside solar activity records. Some of these studies find weak but persistent correlations between geomagnetic storm periods and slight increases in earthquake frequency, not causation. Not proof, just patterns in the noise that show up often enough to make researchers wonder if they're missing something. Other studies find no correlation at all, or find correlations that disappear when you adjust for multiple statistical testing, or find that the apparent patterns reflect human psychology's tendency to notice coincidences while ignoring the vast majority of earthquakes that happen with no solar activity whatsoever. Alaska's current seismic swarm adds another layer to this puzzle. The swarm involves hundreds of small earthquakes clustering in a specific region over a short time period. Swarms are different from main shock aftershock sequences. They don't necessarily have one big event followed by diminishing smaller ones. Instead, they represent ongoing stress adjustments, magma movement, or fluid migration through fractured rock. Alaska experiences these swarms regularly because it sits at the boundary where the Pacific Plate dives beneath the North American Plate, creating one of the most seismically active zones on the planet. The region has produced magnitude 9 earthquakes in historical times. It has the tectonic potential for world-changing seismic events that would make the magnitude 6.0 in Japan look like a warm-up act. So is the current swarm related to the incoming solar storm? The timing coincidence is there. The geographical positioning in the auroral zone, where geomagnetic effects concentrate, adds another layer of intrigue. But correlation isn't causation, and coincidence isn't conspiracy. Thousands of earthquakes happen every day worldwide. Most go unnoticed because they're too small or too remote to affect anyone. We notice the ones that happen near population centres, or during periods when we're already paying attention for other reasons. This is selection bias, the human tendency to see patterns where randomness exists, because our brains evolved to detect patterns even at the cost of occasionally hallucinating connections that aren't real. Yet some researchers persist in exploring possible mechanisms. One hypothesis suggests that geomagnetic disturbances could modulate electromagnetic stresses in Earth's crust, in ways that might influence already loaded fault systems. The idea is that charged particles interacting with the ionosphere could induce currents in conductive rock layers, creating subtle electromagnetic perturbations that propagate downward. In fault zones already at critical stress thresholds, these tiny additional influences might theoretically provide the final nudge that triggers rupture. It's speculative. It lacks direct observational evidence. The energy scales involved still seem too small to matter, but it's the kind of hypothesis that's difficult to definitively disprove, which keeps it alive in certain research communities. Another line of inquiry focuses on the auroral zones themselves. These regions, roughly encircling the magnetic poles at latitudes where auroras regularly appear, also happen to overlap with some of Earth's most active tectonic boundaries. Is this meaningful? Probably not, but it's interesting. The auroral zones mark where Earth's magnetic field lines provide direct access from space to the upper atmosphere. They're where geomagnetic energy gets deposited most intensely during storms, and they include places like Alaska, Iceland, and parts of the Pacific Ring of Fire. The correlation might be pure coincidence, a geographical overlap with no physical significance, or it might hint at processes we don't understand yet, subtle ways that external electromagnetic inputs interact with internal geological processes. The historical record doesn't provide clear answers. Researchers have looked back at major earthquakes and cross-referenced them with solar activity records going back centuries. The 1906 San Francisco earthquake, for instance, occurred during a solar minimum period when the sun was relatively quiet. The magnitude 9.5 Chilean earthquake of 1960 happened during solar cycle 19, a fairly active period, but 2 years after the cycle's maximum. The magnitude 9.1 Tohoku earthquake in 2011 that triggered the Fukushima disaster occurred during solar cycle 24's rising phase. Some studies claim to find correlations in these patterns, others find nothing but noise. The data quality degrades rapidly as you go back in time, making definitive conclusions impossible. What we can say with confidence is that earthquakes don't need solar triggers. They happen with or without geomagnetic storms because tectonic stress accumulation is an internal Earth process operating on its own timescale. The Pacific Plate keeps diving beneath the North American plate regardless of what the Sun does. The stress keeps building, the rock keeps deforming. Eventually something has to give, and when it does, the energy releases in seconds what took decades or centuries to accumulate. Whether that moment of rupture happens to coincide with a solar storm is, in most cases, coincidental. The fault was going to break anyway. The timing is random chance. But could there be edge cases? Could there be specific scenarios where external triggers matter? Volcanoes provide an instructive analogy. They erupt primarily because of internal magmatic processes, pressure buildup in chambers beneath the surface, gas content in the magma, structural weaknesses in the surrounding rock. But external triggers can matter at the margins. A nearby earthquake can jostle a magma chamber that was already primed to erupt. Changes in atmospheric pressure or tidal forces can provide the final push that initiates an eruption that was already imminent. The trigger doesn't cause the eruption in any meaningful sense. The volcano was going to erupt anyway. The trigger just determines the precise moment. Could geomagnetic storms serve a similar role for earthquakes in very specific circumstances? It remains an open question with no clear answer. The scientific consensus leans heavily toward no. The fringe researchers who keep investigating keep looking for that one data set, that one mechanism, that one undeniable piece of evidence that would force mainstream science to reconsider. So far they haven't found it. But as we watch Alaska's swarm continue to build, as we track the plasma screaming toward us from the sun, as we count down the hours until impact, the question hangs there like an itch you can't quite scratch. What if we're missing something? What if Earth's systems are more interconnected than we assume? What if the boundary between space weather and ground-shaking geology is more permeable than our current models suggest? Earth floats inside a magnetic bubble roughly 10 times wider than the planet itself. This magnetosphere, generated by currents of molten iron sloshing around in Earth's outer core, extends into space like an invisible shield, deflecting most of the solar wind that would otherwise strip away our atmosphere. Without it, we'd look like Mars, dry, dead, and scoured by radiation. With it, we get to have an atmosphere, liquid water, and complex life that occasionally builds telescopes to study the very phenomena trying to kill it. It's a pretty good deal as far as magnetic fields go. The magnetosphere isn't a perfect sphere. The solar wind compresses it on the day side, squishing it down to that 10 Earth radii distance we mentioned, while stretching it into a long tail on the night side that extends hundreds of Earth radii downstream. It's shaped like a teardrop or a comet, always pointing away from the sun, always responding dynamically to changes in the solar wind. Most of the time, this happens quietly. The solar wind flows around us, the magnetosphere deflects it smoothly, and life on the surface continues without noticing the cosmic forces at play overhead. Then a coronal mass ejection arrives, and everything changes. The suddenly enhanced solar wind pressure compresses the magnetosphere inward. That nice 10 Earth radii standoff distance shrinks to 7 or 6 or even fewer during intense storms. Satellites that normally orbit safely inside the protective bubble suddenly find themselves exposed. But compression alone isn't the real danger. The real danger comes from magnetic reconnection, a process that sounds technical but has consequences that are anything but academic. Magnetic reconnection happens when magnetic field lines with opposite orientations get pushed together and suddenly snap and reconfigure. It's like two rubber bands stretched in opposite directions getting close enough to interact. They break, reconnect in new configurations, and in the process release tremendous amounts of stored magnetic energy as kinetic energy of charged particles. When a coronal mass ejection's magnetic field points southward, opposite to Earth's northward pointing field, reconnection happens on the day side of the magnetosphere. Field lines that were separate suddenly link up, creating openings that allow solar wind plasma to flow directly into the magnetosphere, instead of being deflected around it. This is when the real show starts. The injected plasma gets accelerated along Earth's magnetic field lines, funneled toward the poles, and slammed into the upper atmosphere at speeds that would make your eyes water. Atoms and molecules in the thermosphere get excited, jump to higher energy states, and then relax by emitting light. We call this light the aurora. From the ground, it looks magical. From space, it looks like planetary self-defense. From the perspective of the charged particles involved, it's the universe's way of disposing of excess energy. But not all the injected plasma makes it to the atmosphere. Some gets trapped in Earth's radiation belts, those toroidal regions circling the planet at altitudes from a few hundred to tens of thousands of kilometers. The Van Allen belts, named after their discoverer, contain populations of electrons and protons bouncing back and forth between the magnetic poles like beads on an invisible string. During geomagnetic storms, these populations swell. New particles get injected. Existing particles get accelerated to higher energies. The radiation environment that satellites have to survive suddenly becomes orders of magnitude more intense. This is where geometry matters more than raw power. A massive coronal mass ejection with perfect southward magnetic orientation can produce more intense effects than a much larger one with northward or mixed orientation. The Carrington event of 1859, the most intense geomagnetic storm in recorded history, happened because a coronal mass ejection with perfect geometry hit Earth's magnetosphere at just the right angle, with just the right magnetic configuration. If that same storm happened today, estimates suggest trillions of dollars in damage to power grids, satellite networks, and electronic infrastructure. And it was caused by a solar event that, by modern standards, wasn't even the largest flare on record. The M7.1 flare that launched our current incoming coronal mass ejection erupted from active region 4324. Sunspots are magnetic battlegrounds where the sun's internal magnetic field breaks through the surface, creating cooler, darker regions that host intense magnetic activity. Active region 4324 has been rotating across the sun's Earth-facing hemisphere for days, occasionally producing smaller flares, building up magnetic complexity, storing energy in twisted field configurations that eventually have to release. The M7.1 flare was one such release, but probably not the last. Here's something most forecasts don't emphasize. Active regions don't suddenly become inert after producing one flare. They continue to evolve, continue to store energy, continue to pose risks for additional eruptions. Active region 4324 is still there, still magnetically complex, still capable of producing follow-up events. If another coronal mass ejection launches while the first one is still impacting Earth, the effects could compound in ways that single event models don't predict. This is another version of the double stack scenario, except instead of two plasma clouds merging in interplanetary space, you'd have sequential impacts with overlapping effects. The official forecasts simplify these complexities into manageable categories, because that's what forecasts are supposed to do. They provide actionable information to technical communities that need to know whether to worry or not. But in simplifying, they sometimes obscure the full picture. Are we underestimating the current situation by treating it as a single, moderate storm? Are there signatures in the data that suggest more complex scenarios playing out? The raw observations are available to anyone with the technical skills to interpret them. Solar images, magnetometer readings, plasma measurements from upstream satellites, all streaming in real time. Most people don't have those skills or the time to acquire them. They rely on experts to interpret the data and provide summaries, and most of the time that works fine. But every once in a while the situation develops in ways that fall outside standard categories. Every once in a while multiple factors align to create something unusual, and when that happens, the simplified forecasts might not capture the full scope of what's unfolding. This is where those firehorse year references and planetary alignment discussions enter the conversation. To be absolutely clear, there is no known physical mechanism by which astrological configurations affect either space weather or earthquakes. The positions of planets relative to Earth don't generate enough gravitational or magnetic influence to matter for these phenomena. These are cultural and historical markers, not scientific variables, yet they capture something important about human pattern recognition and our need to contextualize events within larger frameworks. When multiple unusual things happen simultaneously, we look for explanations that tie them together. Sometimes those explanations are scientific, sometimes they're cultural, sometimes they're wishful thinking or confirmation bias. The challenge is separating meaningful connections from coincidental correlations, real mechanisms from imagined ones, data from noise. As the countdown continues and the plasma approaches, we're left wondering whether we're about to witness a routine space weather event that coincidentally occurred during a period of elevated seismic activity, or whether something more complex is unfolding that our current frameworks aren't equipped to fully understand. What other ideas are floating around in the margins of scientific discourse, just strange enough to dismiss but just interesting enough to keep investigating? Welcome to the frontier, where established science meets intriguing speculation, and not everything comes with peer review stamps and institutional approval. The ideas we're about to explore exist in that strange space between obviously false and not yet proven, where researchers with unconventional approaches chase patterns that mainstream science hasn't bothered investigating, or has investigated and dismissed. Some of these ideas will eventually be validated. Most will be forgotten. A few might revolutionize how we understand Earth's interconnected systems. The trick is knowing which is which before hindsight makes it obvious. Let's start with the Schumann resonances, which sound like something from a science fiction novel, but are actually well-documented electromagnetic phenomena. Earth's surface and the ionosphere, separated by about 60 kilometers of atmosphere, form a spherical cavity that resonates at specific extremely low frequencies. The primary resonance sits at about 7.83 Hz, with additional harmonics at higher frequencies. These resonances are excited by lightning strikes around the world, creating a global electromagnetic background that some researchers believe plays roles in biological processes, atmospheric dynamics, and possibly even consciousness itself, though that last claim ventures well into speculative territory. During geomagnetic storms, the ionosphere's properties change, its altitude shifts, its conductivity varies, and theoretically these changes could modulate the Schumann resonances, altering their frequencies or amplitudes in measurable ways. Some researchers have reported anomalies in Schumann resonance patterns, coinciding with seismic events, suggesting possible connections between electromagnetic phenomena in Earth's atmosphere and geological processes underground. The mechanisms proposed involve piezoelectric effects in stressed rocks, electromagnetic emissions from fault zones, or even more exotic ideas about plasma channels connecting the ionosphere to the lithosphere. The data supporting these connections remains controversial. Multiple studies have looked for correlations and found either weak signals barely above noise levels or nothing at all. The problem with studying Schumann resonances during seismic events is that you're looking for subtle changes in a system that varies naturally all the time. Lightning activity changes, ionospheric conditions fluctuate. Solar influences modulate the background electromagnetic environment constantly. Extracting a specific earthquake-related signal from all that noise requires sophisticated statistical analysis and very careful interpretation. It's easy to find patterns if you're not careful about multiple testing corrections and confirmation bias. But let's say for the sake of exploration that there's something real here. Let's say electromagnetic perturbations in the ionosphere can propagate downward and interact with stressed crustal regions in ways we don't fully understand. What would the mechanism look like? One proposal involves the global electric circuit, a less famous but equally real phenomenon where Earth's surface maintains a negative charge relative to the ionosphere, with thunderstorms acting as generators that maintain the potential difference. During geomagnetic storms, this circuit gets disrupted. The ionosphere's properties change, current flows shift, and maybe, just maybe, these shifts create transient electromagnetic effects that propagate through the crust in regions where conductivity and geometry allow. Another speculative idea focuses on plasma interactions in near-Earth space. When two coronal mass ejections overlap or merge, they create complex plasma structures with unusual properties. The boundary regions between different plasma populations can host instabilities, electromagnetic turbulence, and wave phenomena that don't occur during simple single-event impacts. Some researchers suggest these complex plasma states could generate electromagnetic signals that couple more effectively to Earth's magnetosphere and perhaps even to the ionosphere and surface. It's a cascade of effects, each step requiring specific conditions, but theoretically possible if all the pieces align correctly. The long-term solar cycle stress modulation idea takes a different approach. Instead of looking for immediate triggers, It proposes that the 11-year solar cycle creates subtle biases in Earth's geophysical systems over longer timescales. During solar maximum periods, increased geomagnetic activity, enhanced cosmic ray fluxes, and other space weather effects might accumulate small influences that affect atmospheric circulation patterns, temperature gradients, and eventually crustal stress distributions. It's like water torture, individually insignificant, cumulatively meaningful. The challenge is detecting such subtle effects against the massive background noise of all the other processes affecting Earth systems. Testing these hypotheses properly would require monitoring networks that simultaneously measure space weather parameters, electromagnetic signals at various frequencies, seismic activity, atmospheric conditions, and who knows what else, all with sufficient spatial and temporal resolution to catch subtle correlations if they exist. Some networks approach this level of sophistication, but they're expensive to maintain and generate enormous amounts of data that require careful analysis. Most funding goes to studying phenomena with clearer practical applications or stronger theoretical foundations. Edge theories operate on shoestring budgets and volunteer efforts, which limits how thoroughly they can be investigated. The planetary alignment discussions deserve special mention because they're so popular online despite having zero scientific support. When planets line up in particular configurations, enthusiasts claim increased gravitational or electromagnetic effects that influence Earth. The physics simply doesn't work. Planets are too far away and too small relative to the Sun and Moon to produce measurable additional tidal or magnetic effects on Earth. Jupiter, the most massive planet, has gravitational influence on Earth orders of magnitude smaller than the Moon's tidal effects. Mars's magnetic field is negligible and couldn't affect Earth even if it wanted to. Venus comes closest, but still doesn't pack enough punch to matter, yet people keep looking for planetary alignment correlations with earthquakes, volcanic eruptions, and other geological events. Why? Because alignments are relatively rare and memorable events that create natural anchors for pattern-seeking behavior. When something unusual happens near an alignment, the coincidence feels significant even though thousands of earthquakes happen during periods without alignments that nobody bothers correlating. It's the same cognitive bias that makes horoscopes seem accurate. Vague statements combined with selective attention to apparent hits while ignoring misses. Some enthusiasts have made specific predictions based on these theories. Let's look at their track record honestly. In 2011, various online predictions claimed specific alignment configurations would trigger major earthquakes. Some cited the Tohoku earthquake as validation, ignoring that it happened weeks before the predicted alignment. In 2015, different predictions emerged for supposedly dangerous planetary configurations. Nothing unusual occurred. In 2020, more predictions. Again, nothing beyond normal seismic background. The pattern repeats, predictions get made, earthquakes happen somewhere because they always happen somewhere, and post hoc reasoning claims validation while conveniently forgetting all the failed predictions. This doesn't mean all edge theories are worthless. It means we need rigorous standards for evaluating them. What measurements would support or reject a hypothesis? If Schumann resonance anomalies consistently precede earthquakes, you should be able to predict earthquakes using resonance monitoring. Can you? If plasma interactions during double-stacked coronal mass ejections produce measurable surface effects, those effects should appear in data from previous similar events. Do they? If solar cycles modulate seismic activity, statistical analysis of decades of data should reveal clear correlations after controlling for confounding factors. Do they? The answers so far are mostly negative or inconclusive, which is why these remain edge theories rather than accepted science. But the questions themselves are worth asking. Earth is a complex system with many interacting components. The magnetosphere connects to the ionosphere, connects to the atmosphere, connects to the oceans, connects to the crust. Energy and information flow between these layers in ways we're still mapping. Space weather represents an external input to this system that varies over multiple timescales. It would be stranger if it had absolutely zero influence on any geological processes than if it had small, subtle influences that are difficult to detect and measure. As we move beyond Earth-focused speculation toward broader astronomical contexts, we're left with a methodological question. How do we investigate ideas that are plausible enough to warrant attention, but lack sufficient evidence to justify major research investments? how do we maintain scientific rigor while staying open to discovering connections we didn't expect? The history of science includes many examples of initially dismissed ideas that later proved correct, but it includes vastly more examples of dismissed ideas that deserve dismissal. The challenge is developing good filters that catch the rare gems while efficiently rejecting the abundant nonsense. Speaking of unexpected discoveries, what's happening in the outer solar system right now challenges our understanding of planetary formation in ways that might be relevant to how we think about complex systems in general. Everything you learned about the outer solar system might need revision. For decades, astronomy textbooks divided planets into neat categories: rocky inner planets like Earth and Mars, gas giants like Jupiter and Saturn, and ice giants like Uranus and Neptune. The ice giant designation reflected our understanding that these distant worlds contain substantial amounts of water, methane, and ammonia ices in their interiors, surrounding relatively small rocky cores. It was a tidy classification scheme that helped organize the solar system into understandable chunks. Except new research suggests it's wrong. Uranus and Neptune might not be ice giants at all. They might be rock giants, with interiors dominated by rocky and metallic material, rather than the icy layers we've long assumed. This revelation comes from careful analysis of multiple data sources that individually seemed insignificant but collectively paint a different picture. Gravity measurements from spacecraft flybys, combined with improved models of planetary interiors, suggest higher average densities than pure ice models predict. Thermal emission observations show both planets radiating more heat than they receive from the Sun, indicating internal heat sources that require explaining. And most tellingly, their magnetic fields behave strangely in ways that make more sense if their interiors have different compositions and structures than we've been assuming. Let's unpack what the old model said. Ice giants were supposed to have small rocky cores, perhaps a few Earth masses, surrounded by thick mantles of compressed ices. These ices wouldn't be frozen in the sense we think of ice on Earth. At the pressures and temperatures inside Uranus and Neptune, water and methane take on exotic high-pressure forms called superheated ices, where oxygen atoms form a crystalline lattice while hydrogen nuclei flow through it like a liquid. It's a weird state of matter that only exists under extreme conditions, and it was supposed to dominate these planets' interiors, explaining their masses and sizes. The new model suggests something different. They propose that rocky and metallic material makes up a much larger fraction of these planets' masses, potentially 60 to 70% rather than the 20 to 30% the old models assumed. This rocky component would form not a small dense core but an extended interior region, possibly with gradual transitions rather than sharp boundaries between different layers. The ice content would still be significant, but wouldn't dominate the mass budget the way previous models suggested. Why does this matter beyond just getting planetary composition right? Because magnetic fields provide a window into planetary interiors that we can't access any other way. Earth's magnetic field is generated by convecting liquid iron in the outer core, creating a dipole field that aligns roughly with the rotation axis and extends into space to form that protective magnetosphere we discussed earlier. Jupiter and Saturn have similar dipole-dominated fields, though much stronger than Earth's, but Uranus and Neptune have bizarre multipolar fields that don't align with their rotation axes and look nothing like simple dipoles. Voyager 2, the only spacecraft to visit these planets, measured their magnetic fields during brief flybys in the late 1980s. The data showed Uranus's magnetic field tilted 59 degrees from its rotation axis, while Neptune's is tilted 47 degrees. Both fields have strong quadrupole and octopole components, creating complex geometries that would make compass navigation impossible. For decades, scientists struggled to explain these strange fields using the ice giant model. The proposed mechanisms involved shallow conducting layers of superheated ice generating fields through unusual convection patterns, but the models never quite worked satisfactorily. Rock-dominated interiors offer better explanations. If the planet's conductive regions have different geometries and compositions than assumed, the observed magnetic field structures become easier to generate through standard dynamo processes. The tilt and complexity could arise naturally from the interaction between rocky cores, conducting icy layers, and the planet's rotation. It's not a perfect explanation yet, but it's more promising than the previous attempts that always seem to require special pleading and fine-tuning. The implications extend beyond Uranus and Neptune themselves. Planetary formation theory has always struggled somewhat with the ice giants. They sit in a region of the solar system where our models say planet formation should have been slower and less efficient than where Jupiter and Saturn formed. Yet somehow these two substantial worlds came together before the solar nebula dissipated. If they're actually rock giants with captured ice envelopes rather than grown ice planets, the formation scenarios might work better. Perhaps they formed closer to the Sun where rocky material was abundant, then migrated outward to their current orbits, capturing ice as they went. This connects to exoplanet research in fascinating ways. We've discovered thousands of planets around other stars, many with masses and sizes similar to Uranus and Neptune. These Neptune mass exoplanets are among the most common we've found, suggesting they form readily under a wide range of conditions. If our local examples are actually rock-dominated rather than ice-dominated, it affects how we interpret observations of those distant worlds. Spectroscopic measurements of exoplanet atmospheres might be telling us different things than we thought. Density measurements might imply different interior structures. The entire population of Neptune-mass planets in the galaxy might need reclassification. There's something philosophically satisfying about discovering that even in our own solar system, in our cosmic backyard, we still have fundamental misunderstandings about the nature of entire worlds. Uranus and Neptune orbit about 2 and 3 billion miles from the Sun, respectively. We've studied them through telescopes for centuries. We've sent spacecraft to visit them. We've analysed every photon of reflected sunlight we can capture. And yet we apparently got their basic composition wrong because we were working from incomplete data and making reasonable assumptions that turned out to be incorrect. This connects back to our theme in a sideways but meaningful way. Complex systems often hide their true nature behind surface appearances. Earth's magnetosphere looks like a smooth protective bubble from most visualizations, but it's actually a turbulent dynamic structure with complex internal processes we're still discovering. The solar wind looks like a uniform flow in simplified models, but it's full of structures, discontinuities, and interaction regions that matter for actual predictions. And apparently Uranus and Neptune look like ice giants, from simple observations but reveal rock giant characteristics when examined more carefully. The lesson is that reality is usually more complex than our models, and we should remain humble about what we think we know versus what we've actually proven. As we approach the final hours before our incoming coronal mass ejection arrives, as we continue monitoring Alaska's seismic swarm and watching for any additional signals that might connect these phenomena, it's worth remembering that our understanding of the cosmos is always provisional. We build models based on available data. We make predictions based on those models, and then nature does what it does, sometimes confirming our models, sometimes revealing gaps we didn't know existed. The real question isn't whether we'll ever achieve perfect understanding. The question is whether we're asking the right questions and using the right tools to improve our understanding over time. Speaking of tools, there's one type that's revolutionizing how we explore these questions. Machines are learning to see patterns humans miss. This isn't a dystopian warning about artificial intelligence replacing scientists. This is a genuinely exciting development about using computational tools to accelerate discovery in ways that complement human insight rather than replacing it. In the past few years, machine learning algorithms trained on vast datasets of astronomical observations have started identifying rare cosmic events, classifying unusual spectral signatures, and detecting subtle patterns that would take humans years to find manually. And some of these discoveries are directly relevant to the topics we've been exploring. Consider space weather forecasting, which currently relies on physics-based models that simulate the solar wind's interaction with Earth's magnetosphere. These models are sophisticated but computationally expensive, requiring supercomputers to run and producing forecasts with inherent uncertainty ranges. Machine learning offers a complementary approach. Train algorithms on decades of historical data showing solar observations, solar wind measurements, and resulting geomagnetic conditions. The algorithms learn patterns connecting precursor signals to outcomes without needing to understand the underlying physics. They don't replace physics-based models, they supplement them, sometimes catching patterns the physics models miss. Recent research has demonstrated this potential. Neural networks trained to predict geomagnetic indices from upstream solar wind measurements sometimes outperform traditional models, especially for unusual events that fall outside standard categories. They're not magic, They're pattern recognition engines optimized through massive computational effort, but when they work, they can provide earlier warnings or catch edge cases that simplified models overlook. For our hypothetical double-stacked coronal mass ejection scenario, an AI system trained on rare multi-structure events might recognize signatures in the data that human forecasters or standard models would miss. Machine learning tools trained on thousands of comet spectra can flag these outliers automatically and rank them by how unusual they are. This doesn't tell you what the unusual object is, but it directs human attention to where it's needed most. Consider an interstellar object like 2E Borisov, the second confirmed interstellar comet that visited our solar system in 2019. Its spectrum showed both familiar and unusual features. AI classification tools helped astronomers quickly identify which aspects were truly anomalous versus which just reflected its extrasolar origin. This accelerated follow-up observations and analysis during the brief window when the object was observable. For solar flare prediction, several research groups are developing AI systems that analyze magnetograms, images showing magnetic field strengths and orientations across the sun's surface. Active regions with complex twisted magnetic configurations are more likely to produce flares, but predicting exactly when a flare will occur and how strong it will be remains incredibly difficult. Human experts examine magnetograms and issue predictions based on experience and pattern recognition. Machine learning systems can now match or sometimes exceed human performance by identifying subtle precursor signatures in the magnetic field, evolution hours or days before eruptions. The process isn't foolproof. AI systems make mistakes. They produce false positives, flagging events that never materialize. They occasionally miss real events because the precursor signatures fall outside their training data, and they're opaque. Even when they work, understanding why they made a particular prediction can be challenging because the decision process involves thousands of weighted parameters interacting in complex ways. It's like asking someone how they recognize faces. They do it effortlessly, but can't explain the process step by step. Neural networks trained for pattern recognition face similar challenges in interpretation. This opacity creates legitimate concerns. When an AI system predicts a major solar storm with potential infrastructure impacts, decision makers need to understand the basis for that prediction. Is it built on solid physical reasoning that happens to be encoded in network weights? Or is it spurious correlation that worked on training data but will fail on new events? Developing methods to interpret and validate AI predictions remains an active research area. Techniques like attention visualization, which shows what parts of input data the network focused on when making decisions, help somewhat. But we're still learning how to trust these tools appropriately. Another application involves spectral analysis of unusual objects. Remember 3I Atlas, the interstellar object that might or might not be a comet, that generated debate about its composition and origin? Spectroscopic observations of such objects produce data that human experts must analyze to infer composition. But subtle features can be missed, especially in noisy data or when the object is faint. Machine learning tools trained on spectral libraries can identify weak absorption or emission features that might indicate unexpected molecules or unusual abundances. The same techniques apply to analyzing electromagnetic signatures in Earth's ionosphere and magnetosphere. During geomagnetic storms, satellites measure fields and particle populations that vary rapidly in complex ways. Identifying unusual patterns that might indicate something like our hypothetical double-stacked plasma impact requires sifting through enormous datasets. Machine learning algorithms can flag anomalies automatically, directing human attention to interesting time periods for closer examination. They act as intelligent filters, separating potentially significant signals from routine background. As our countdown to coronal mass ejection impact reaches its final hours, as monitoring stations around the world prepare to measure whatever arrives, as we wonder whether Alaska's seismic swarm will continue building or dissipate, the tools we're using to understand these phenomena continue evolving. We're not just watching space weather anymore. We're deploying increasingly sophisticated computational approaches to extract meaning from observations, identify anomalies in real time, and perhaps catch early signals of phenomena we haven't fully characterized yet. The universe is vast, complex, and full of interconnected systems operating on scales from subatomic particles to galactic structures. Our understanding remains incomplete, our models remain approximations, but our tools keep improving, our questions keep sharpening, And occasionally, nature surprises us with discoveries that force us to revise what we thought we knew. Maybe tomorrow's plasma impact will be routine. Maybe it will reveal something unexpected. Either way, we'll be watching, measuring, analysing and learning. Because that's what humans do when faced with mysteries. We investigate, we question, and we keep pushing the boundaries of understanding, one discovery at a time. The cosmos doesn't care whether we understand it or not, but we care, and that caring drives us to keep looking up, keep asking questions, and keep searching for connections between the sun's fury, Earth's restless geology, and the deeper patterns that might unite them into a more complete picture of how our cosmic neighbourhood actually works.